Hello all. Today we'll see the critical section problem in operating system. We'll discuss how the problem occurs and what do you mean by critical section. So critical section is the part of process where the code for accessing the shared resource is written. That part or session is the critical section of that process. So this is a code where number of process want to execute that code of that process, and executing that code simultaneously by number of process may create inconsistency of the data in that execution. So as we see, multiple process in the system and these process access shared resource, but simultaneous execution may create inconsistency in that. So we have to avoid that. So we must use some synchronization mechanism to avoid this kind of problem. So you can see the example for this. Suppose P0 and P1 both of the process share the code for the execution, that is reading the variable value A, increment the value of variable by 1 and write the variable value A. So in that case you can see if the process P0 execute first and P1 execute second. So in that case, process P0 read the variable of A equal to 0, increment it by 1, so it become 1 and write back. In the next execution, now process P1 read the variable value A equal to 1, it increment its value by 1, it becomes 2 and write the value of incremented value as 2. So after this, both process P0 and P1 finish accessing the variable A. The value of A is 2. We can see the second case of execution, like P0 has read the variable A equal to 0 and suddenly context switch happens and P1 take the charge and start executing the process. P1 would increment the value of A and it becomes A is equal to 1. In the second step, after execution, P1 gives the charge again to P0. Now the value of A for P0 is 0, as it has read that particular value and context switch was occurred. And when it start executing, it would increment the value of A from 0 to 1. So here both process P0 and P1 end up accessing the variable A, the value of A equal to 1, which is different from the value of A equal to 2 in the first case. So you can see in the first case the result was 2 and in the second case the result is 1. So we can see the output of this execution is depending upon the order of execution of the processes. So that sequence of execution of process affects the result, and this situation is called as a race condition. So number of process require the access of shared resource for execution, and they are in race to access that particular shared resource. This is called as a race condition, and it affect on the value or output of that particular execution. So consider in the critical section problem, number of processes are there, P0 to Pn, and each of the process has segment of code called critical section, in which the process may be changing common variable or updating a table, writing a file, and so on. The important feature of the system is that when one process is executing in its critical section, no other process is to be allowed to execute in its critical section. So the execution of critical sections should be mutually exclusive. Means if one process has entered in the critical section, in its critical section, no other process can execute that part of the code until earlier process has left that particular execution. So you can see the structure do while loop, in that the entry section, some condition is written in that entry section to the critical section. If it is satisfied, the process can enter into the critical section. It execute in the critical section and it exit from the critical section after execution. It execute reminder section and it goes on. Solution to critical section problem, we can see mutual exclusion. In this, the hardware instruction must verify that at a point in time only one process can be in its critical section. So we have to see that no two process or more than one process will be in its critical section, so that the shared resource will not create an inconsistent result of execution. Second, bounded waiting. The process interested to execute their critical section must not wait for long time to enter their critical section. And progress, the process not interested in entering its critical section must not block other processes from entering into their critical section. Critical section handling in OS, it is done by two approaches. Two approaches are available. Preemptive, it allows preemption of process when running in kernel mode, and in non-preemptive, runs until exits kernel mode or block the process, or voluntarily it leaves the CPU execution, and it is essentially free of risk condition in the kernel mode. You can see the first part. To achieve the synchronization and to avoid the critical section problem, this is mutual exclusion with the help of hardware support. So synchronization hardware is a hardware based solution to resolve the critical section problem. How the multiple process sharing common resource must be synchronized to avoid inconsistent result. The hardware instruction that can be used to resolve the critical section problem efficiently. So it gives some instructions to achieve the synchronization, and the hardware based solution to critical section problem is based on a simple tool, that is lock. So this solution makes sure that before entering into the critical section, the process must acquire a lock and must release the lock when it exits its critical section. So using of lock also prevent the rest condition. So the structure of this do while, in that acquire lock. This is the entry condition to the critical section. Then execute in the critical section. After completing that part, release the lock and execute the reminder section. And we have two instructions, test and set and swap. These hardware instructions are available which provide the synchronization while executing the critical section. So mutual exclusion using test and set hardware instruction. You can see this instruction can be implemented to achieve mutual exclusion, bounded wait and progress. So in the example we can see the global boolean variable lock, and it is initialized to false. Consider we have two processes P0 and P1 are interested to enter their critical section. So the structure for achieving mutual exclusion is as follows. We can see do while test and set ampersand lock, and semicolon is given after this parenthesis. So here test and set ampersand lock. If lock is set to true, it gives true result, and while the lock is true, it will execute the while loop. It will not enter into the critical section. If the lock is equal to false, the while loop execution return the false result, and it will break that particular loop while loop statement, and it enters into the critical section. So we can find the process want to enter into its critical section should check the value of lock. If it is false, the process can enter into its critical section and set the lock to true. Okay, it set the lock value to true. It enter into the critical section. It execute in the critical section, and it set the value of lock is equal to false whenever it has completed the execution. It comes out of critical section, execute reminder section. So it happens globally declare a boolean variable lock and initialize it to false. P0 and P1 are interested to enter their critical section. Let us say P0 want to enter the critical section, it execute. So as we have seen, it execute the while loop, test and set ampersand lock condition. As it is false, it return the false result in the while loop, and it can enter into its critical section. So it set the value of lock to true, it execute the critical section. After finishing that, it set the value of lock to false, and it comes out of that particular critical section. So now P1 can check the value of lock as it want to enter in its critical section. So it find the lock value is equal to false. So it it make the value of lock as a true and enter into the critical section. So using this mechanism, we can achieve the synchronization in the execution of critical section. So this is the solution to obtain synchronization in this execution. The swap hardware instruction like test and set instruction, the swap hardware instruction is also an atomic instruction. Atomic means it has, if the process has entered into its critical section, it has to execute all statement which are there in the critical section. It cannot stop the execution. So that is atomic. So generally the statements are read the value of variable, then update the value of the variable, and write the value of updated variable. So with a difference that it operates on two variables provided in its parameter, the structure of swap instruction is in the do while loop, key is equal to true while key is equal to false, as it is not a semicolon after this while loop. If the condition is true, it executes in the while loop, that is swap ampersand lock and key. So here ampersand lock, key is equal to true and lock is the value of lock is set in initially. So if it is true, then it enters into the critical section, and it is setting the value of lock as a false, and after it execute the remainder section. So this is the swap instruction executed. So to achieve this using swap, the structure above operates on one global shared boolean variable lock and another local boolean variable key, both of which are initially set to false. The process P0 interested in executing its critical section execute code above and set lock as true and enter to its critical section, and it will block other process from executing into their critical section, satisfying the mutual exclusion. So this is how we obtain the synchronization, and we can execute, the process can execute only one process can execute in its critical section, so that it can avoid the inconsistency in the given problem. So today we complete critical section problem, and we achieve the solution to the critical section problem using hardware solution, test and set instruction, and swap instruction. Remaining points we'll see in the next part.